The universe is vast and filled with wonders. Among them are nebulae, immense clouds of gas and dust. These cosmic clouds drift through space, often appearing as luminous and colorful displays when illuminated by nearby stars. Nebulae are not just beautiful sights, they are stellar nurseries, the birthplaces of stars like our Sun. Imagine a cold, dark cloud of hydrogen and helium, remnants of the early universe. This cloud, a nebula, is not uniform. It has regions of slightly higher density where gravity begins to exert its pull. Over vast spans of time, these regions draw in more and more gas and dust. As more material falls inward, the core of the collapsing cloud heats up. This dense, hot core is a protostar, the earliest stage in a star's life. The protostar continues to grow, accumulating mass and increasing in temperature, setting the stage for the next dramatic phase in its evolution. Deep within the collapsing nebula, the protostar grows hotter and denser. Gravity relentlessly pulls material inward, increasing pressure and temperature at the core. The protostar is not yet a true star, as it does not generate energy through nuclear fusion. Instead, it glows with the heat generated by the gravitational collapse of its own matter. As the protostar evolves, it spins faster and faster due to the conservation of angular momentum. Think of a figure skater pulling their arms in to spin faster. This rapid rotation flattens the cloud of gas and dust surrounding the protostar into a swirling disk, known as a protoplanetary disk. Within this disk, the seeds of planets begin to form. Dust grains collide and stick together, gradually growing into larger and larger objects. Over millions of years, these clumps can become planets, asteroids, and comets, all orbiting the central star. Deep within the heart of the protostar, a critical threshold is about to be crossed. This is a moment of transformation where the very nature of the protostar will change forever. The temperature and pressure become so intense that hydrogen atoms, the simplest and most abundant element in the universe, are forced to fuse together. This fusion process is not just a simple combination. It is a powerful reaction that alters the fundamental structure of matter. This process, called nuclear fusion, releases an incredible amount of energy. The energy produced is so immense that it powers the star, allowing it to shine brightly for millions or even billions of years. In nuclear fusion, 4 hydrogen nuclei combine to form one helium nucleus. This transformation is a cornerstone of stellar evolution, marking the birth of a new star. The mass of the helium nucleus is slightly less than the combined mass of the 4 hydrogen nuclei. This small difference in mass is crucial to the process. This tiny difference in mass is converted into a tremendous amount of energy, according to Einstein's famous equation, E equals mc squared. This equation explains how a small amount of mass can be transformed into a vast amount of energy. This energy, in the form of light and heat, radiates outward from the core. It travels through the layers of the star, eventually reaching the surface and beyond. It pushes against the inward pull of gravity, creating a delicate balance. This balance is essential for the star's stability, preventing it from collapsing under its own gravity. The protostar is no longer just a collapsing cloud of gas. It has become a star, shining brightly with the power of nuclear fusion. This marks its transition to a main sequence star, a new phase in its stellar journey. Our Sun, a yellow dwarf star, has been steadily fusing hydrogen into helium for about 4.6 billion years. This process is what powers the Sun and allows it to shine so brightly in our sky. This period of stability, where a star generates energy through hydrogen fusion in its core, is called the main sequence. It's a phase that most stars, including our Sun, go through during their lifetimes. The Sun will spend approximately 90% of its life in this stable phase, which translates to billions of years. This long period of stability is crucial for the development and sustenance of life on Earth. During the main sequence, the outward pressure from nuclear fusion balances the inward pull of gravity. This delicate balance is what keeps the Sun stable and prevents it from undergoing drastic changes. This balance keeps the Sun from collapsing under its own weight or expanding outward uncontrollably. It's a finely tuned equilibrium that has been maintained for billions of years. The Sun's energy output is remarkably constant, providing a stable source of light and heat for life to flourish on Earth. This consistency is vital for maintaining the conditions necessary for life. The Sun's energy is not only essential for life on Earth, but also drives the weather patterns. ocean currents and many other processes on our planet. Without the sun's energy, Earth would be a very different place. It is the ultimate source of energy for almost all life on Earth, either directly through photosynthesis or indirectly through food chains. The sun's influence extends to every corner of our planet, making it the cornerstone of life as we know it. Section 5. The red giant, a star, expands. After billions of years of stable hydrogen fusion, the sun will begin to run out of fuel in its core. As the hydrogen fuel depletes, the outward pressure from nuclear fusion will decrease. Gravity will begin to win the battle, causing the sun's core to contract and heat up even further. This heating of the core will cause the sun's outer layers to expand dramatically, transforming it into a red giant star. The sun will swell to an enormous size, engulfing the orbits of Mercury, Venus, and possibly even Earth. As the sun expands, its surface temperature will cool, giving it a reddish appearance. Despite its cooler surface, the sun's luminosity will increase significantly, bathing the inner solar system in intense heat and light. Section 6. Planetary Nebula, a cosmic masterpiece. As the red giant sun continues to evolve, its core will become extremely hot and dense. Helium, the product of hydrogen fusion, will begin to fuse into heavier elements like carbon and oxygen. This process will release even more energy, causing the sun's outer layers to become unstable and eventually be ejected into space. The ejected material will form a glowing shell of gas and dust around the sun, creating a spectacular cosmic phenomenon known as a planetary nebula. Planetary nebulae have nothing to do with planets. They were misnamed by early astronomers who observed their round shapes through telescopes. Planetary nebulae are relatively short-lived, lasting only tens of thousands of years. However, during their brief existence, they enrich the interstellar medium with heavy elements, seeding the universe with the building blocks of future stars and planets. Section 7. White dwarf, cooling ember of a star. After the sun sheds its outer layers as a planetary nebula, its hot, dense core will be exposed. This remnant core is called a white dwarf. White dwarfs are incredibly dense objects, about the size of Earth, but containing a mass comparable to the sun. A white dwarf no longer generates energy through nuclear fusion. Instead, it shines with the residual heat from its long life as a star. Over billions of years, the white dwarf will slowly cool and fade, eventually becoming a black dwarf. A cold, dark object barely detectable in the vastness of space. White dwarfs are the final evolutionary stage for stars like our Sun, those not massive enough to become neutron stars or black holes. They represent the end of a star's life cycle, but their story does not end there. Section 8. Stellar ashes, the cosmic cycle continues. Even though a white dwarf represents the end of a star's life, it is not the end of the story for the matter that once made up that star. The material ejected into space during the red giant and planetary nebula phases is rich in heavy elements, forged in the star's core through nuclear fusion. This material, enriched with the building blocks of life, will eventually mix with the interstellar medium, becoming part of new nebulae. Over vast stretches of time, these nebulae will give birth to new stars and planetary systems, continuing the cosmic cycle of stellar evolution. The atoms that make up our bodies, the Earth and everything around us, were once part of stars that lived and died long ago. We are all made of star stuff, and the sun's life cycle is a reminder of our deep connection to the cosmos. Section 9. A universe of stars, reflections on our sun. The sun's life cycle is a dramatic story of birth, life, death, and rebirth. It begins in a stellar nursery, where clouds of gas and dust coalesce under gravity to form a new star. This process is both violent and beautiful, as the forces of nature work in harmony to create a new source of light and energy. It is a story that plays out on a cosmic scale over billions of years, shaping the universe as we know it. Stars are born, live out their lives, and eventually die, often in spectacular explosions that seed the cosmos with the elements necessary for new stars and planets to form. By understanding the sun's life cycle, we gain a deeper appreciation for our own place in the cosmos. The sun is not just a source of light and warmth, it is a dynamic and evolving entity that has a profound impact on the entire solar system. We are fortunate to live during a time when our sun is in its stable main sequence phase, providing the energy necessary for life to thrive on Earth. This phase, which lasts for billions of years, is characterized by the steady fusion of hydrogen into helium in the Sun's core. However, the Sun's life cycle is a reminder that nothing lasts forever. Eventually, the hydrogen in the Sun's core will be depleted, and it will enter the next phase of its evolution. Billions of years from now, our Sun will evolve into a red giant, dramatically altering the solar system. During this phase, the Sun will expand to many times its current size, engulfing the inner planets and possibly even Earth itself. While the eventual fate of the Sun may seem like a distant concern, it highlights the importance of exploring and understanding the universe around us. By studying the life cycles of other stars, we can gain insights into the future of our own Sun and the potential impacts on our solar system. By studying stars of all ages and stages of evolution, we can piece together the cosmic timeline and gain a deeper understanding of our own origins and destiny. Each star tells a part of the story, contributing to our knowledge of how the universe has evolved over time. The universe is a vast and wondrous place, and the Sun's life cycle is just one of its many captivating stories. As we continue to explore the cosmos, we uncover more about the intricate and interconnected nature of all celestial bodies, deepening our appreciation for the beauty and complexity of the universe.